Hello, in this video I'm going to talk a bit about conditional probability and independent events. Now, whenever we talk about uh, independent and dependent events, the main thing is that we have to establish uh, kind of like the vocabulary as to what does it mean to be independent and what does it mean to be dependent. So, for example, we say that two events, E and F, are independent. So we could say like E and F are independent if, okay, so we'll say like this, the occurrence. So we have to have that the occurrence of event E does not affect the occurrence or the probability of event F. Okay. Now normally we'll just kind of say that as long as the events really have no effect on each other, then we can say that they are definitely independent. Such as like if we say that A is the event that I flip a coin and it lands on heads, and B is the event that it snows tomorrow. Well, whether the coin lands on heads or not, it doesn't really affect whether or not it's going to snow tomorrow. So in any case, like we would say that those two events are independent. Now, similarly, we would say that a sets of E and F, or events E and F, are actually dependent if the occurrence of event E in a given probability experiment affects the probability of event F. Now, we can probably just, kind of consider a particular example. So, let's say that a card is drawn. From a 52 card deck. And then a die is rolled. Okay, now if we have that a card is drawn from a 52 card deck and a die is rolled, well, we can probably say, for example, that let's say that A is the event a heart is drawn. And then we say that B is the event that an odd number is rolled. Okay, now it would actually take a lot to kind of like, outline the event that a heart is drawn, because basically you have that essentially you would have that the event A would basically be like where you're gonna list out every single heart. So like, you would have your ace, you would have the 2, the 3, the 4, the 5, the 6, the 7, the 8, the 9, the 10, and then of course you have the jack, the queen, and the king. Now, the assumption is that all of these are hearts. And then event B is basically that an odd number is rolled. So in that case, you have that, well, you have that, let's just draw it like this. Even though we don't really technically ever draw it like that, we'll just draw it like this. So that way we don't make any confusion as to, um, like if we're gonna say 1, 3, and then 5, it's understood that we don't mean the the values that are on there. So this is 1, 2, 3, 4, and 5. Okay, so these are basically just the outcomes that occur. Now, all putting this to aside, basically we have that these two events are independent because the results of choosing a card really has no impact on the results of the die toss. Okay, so whether or not we draw a heart, no matter the value, 8 hearts or something like that, it's not going to have any effect as to like, what is going to be rolled with event B. Now, usually we can also, indicate, well, what does it mean whenever you have events uh, that may or may not be independent or dependent in either case? You might like wonder like what does that even mean? For instance, for something to be dependent or even independent, like what does that look like? Well, another way that you can kind of think about it is, for example, let's say that you're taking a true-false quiz. Well, if you're taking a true-false quiz, usually you can kind of say that, well, basically, I know that the probability of getting the question correct is a half. So in either case, like, if you had that there were like 10 questions, well, in that case, if you wanted to get all of them correct, well, if you wanted to get all of them correct, then you would know that basically it's just going to be one half because you have one half for the first question, and then for the second, it's the same thing. You would have one half for the second question. But basically, you're going to repeat that process until essentially you've reached the last one. So that's the 10th question, which that's going to be one half. But basically, this would equate to saying that essentially the answer would be that it would be one half raised to the 10th power. Now, the idea is that each question really has no effect. So, like, if this was true, it would still be the same probability essentially for the second, the third, and the fourth, and so on. So we have that in this sense, you have that these are independent set trials that you're just going through the process of finding, like, is it going to be true or false? Well, in this case, you have that the outcome is one half for each time that you potentially would guess. Now, another way that you could kind of think about it is the flip of a coin. So, like if you think about if you flip a coin, then in that case, you have that the probability, similarly, is also one half. Now, of course, if you think about it like this, like if the coin is tossed 3 times, well, you might wonder, for instance, like what is the probability that it doesn't land on your choice? Or let's say like this, what is the probability that it lands at least once? So, like for example, you know that the outcomes are heads, 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 and then you have tails, heads, and then tails. Okay, so I don't want to list out the entire set, but in either case, like, if we were talking about that we have just 3 tosses and basically we want it to land on our choice, maybe just the whole thing, like heads, 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 or tails, tails, tails. So another case, you have the first, the second, then third. So then you think about it like this. Well, the first one is a half, the second one is a half, and the third one is also a half. But that's just going to give you, similarly, just one half raised to the third power. Now, of course, that is an eighth, okay? So make no mistake that that's an eighth, which is like half of 0.25%. So these are also independent because I have that if I flip a coin once and I flip a coin again and again, well, it doesn't affect at all. Now, similarly, if we consider, for example, if you have a deck of cards. Now, let's say that two cards are drawn uh, without, or let's say with replacement. Okay, so we'll say like with replacement. Okay, so we might say probability of getting a, we could probably say like this, like getting a red card if the first was also a red. Okay, so this is kind of interesting because in this case, you have that there's 52 cards, which means that there are 26 red cards, and then you have that there are 26 black cards. Now, in this case, if you think about it like this, um, that if you take the first card drawn, it's going to be a red. So what is that out of? 26 out of 52. But then if you multiply this by the second choice, well, in this case, you have that, um, let me say it like this. Actually, yeah. Let's say without replacement. I'm sorry. So we'll just say without replacement. Okay, so we'll say without replacement, because if I say with replacement, then I'm not really doing anything new technically. So we'll just say without replacement. So after we've drawn our red card on the first, well, the next thing is that you have that there's 25 left. So we have that there's 25 left, and that's out of 51 cards. Now, in that case, that's actually going to be, this is going to be like this because you have that one card is missing, so you have removed it entirely. Because remember that the first red card was already drawn. So it could be two red aces, like a red ace or maybe a red five or something like that. So in either case, what that means is that once that card has been drawn, it's now gone from the count. So in that case, this is an example of a dependent. Okay, so we have that, and I won't go through the trouble of, finding what this computation is. You could probably do that and see like what you get. Um, uh, it might be close to, like 25%. But in other case, like this is just an example of like what it means to be dependent, okay? Because, yeah, the next card does depend on whatever the first is. Now, um, one thing that I want to introduce, though, is this whole idea of, in this next topic, this whole idea of conditional probability. So we have that conditional probability a conditional probability, it actually looks something like this. So consider this: if you have a sample space, okay? So if we have a sample space, and let's just say that this is the universal set. Now, let's say that you have a set A, but then let's say that you have also a set, let's say like just B, for example. So we'll just label this. This is going to be B, and this is going to be A. Now, it's clear that basically that A is a subset of U, and so is B is a subset of U. But more or less, I have that B is a subset of A. Now, whenever we deal with conditional probability, basically we're saying that um, if an event occurs, so like if we have an event that occurs, we can actually look at their intersection where they would overlap. So essentially, a conditional probability is defined in the following manner. You have the probability of B given A is equal to the probability of B and A, but out of the entire probability of A. Now, this would actually be the formula for finding, a conditional probability, for example, and that's A, okay? So this is like one of your formulas, your many formulas. Now, one thing to note is that to find the probability vice versa, so like if you were looking at the probability of A given B, that would actually be the complete opposite. You'd have A intersect B divided by the probability of B. So in this case, you have that this probability has that the B has occurred. Of course, it wouldn't correspond to this diagram necessarily, but that's kind of like what we're going to look at in the remaining of this video is conditional probabilities. Now, conditional probabilities, there are many ways to interpret it really, but really the best way to kind of look at conditional probability is, let's say that, for example, a die is rolled. So you have that a die is rolled. Now, the corresponding sample space would normally be, of course, like 1, 2, 3, 4, 5, and 6. However, let's say that A, let's say that A is the event that a odd number is rolled. Okay, so we have that A is the event that an odd number is rolled. So that's going to be 1, 3, and 5. But let's say that B is the event that a 3 is rolled. Uh, mm, well, let's say like this. Like we have that. Yeah, if a 3 is rolled, then we don't really need to consider really anything. So let's just leave it at that. Okay, so we'll just do that. Now, let's say that I wanted to find the probability. We'll just write it like this. The probability of a 3 given that the number was odd. Okay, so the thing that you have to look at is how many odds are there? There's 3. But then you have to think about, well, what number of outcomes do we have when when the outcome is a 3 and that it's odd? Well, that's really just 1. So it's like 1 out of 3. So we have that the conditional probability for this one would be just 1/3. Now, hopefully you've realized that basically whenever you're looking at a conditional probability, it's essentially making the sample space much smaller or more narrow. But if you look back at the diagram over here, that's exactly what's happening, is that the universal set is right there. The set that lives inside of it is only just a part of it. It's not like the whole thing. So that's like one way that you can look at a conditional probability, is just by looking at their values. Now, another way that we can look at it is essentially is actually just looking at let's say like their formulas, for example. So you might actually have that. Let's say, for example, that you um, let's say that you want to find the probability of B given A when you have that P of B intersect A is equal to, let's say, like 0.35, and then you have that the probability of A is equal to 0.65. So in this case, formulaically, you would actually just go ahead and say, okay, well, essentially we have that all we need to do is just say that we'll take P of B given A is equal to P of B given A, and all of this is divided by P of A. Now, that means that you have 0.35 divided by 0.65. Now, of course, you can actually reduce that nicely just by using any um, just by using like a calculator essentially. So you just have like 0.35 divided by 0.65, and roughly that's going to give you 0.54. Okay, so we have 0.54 would be the answer to that. Now, of course, if I knew what the probability was, I could actually like the probability of B given A already, then it's just a matter of multiplication essentially. So then in that case, like we have that there's yeah, like there's basically what we call something called multiplication rule, which essentially just says that you just have to multiply. So like for example, if I have that if we look back at the formula, so like if you have P of B given A, that's equal to P of B given A, or intersect A, and this is divided by P of A. Essentially, we have that the intersection is equal to P of B, and it's multiplied by A, and this equals to the conditional probability multiplied by the event of P of A. So this would be somewhat of another formula that you would be using. So it gives you this statement right here. Now, one thing though, so we call this the general multiplication rule. Okay, so this is called general multiplication rule, and similarly, if this was a A and that was a B, then you would just kind of move things around essentially. Um, Now, one nice little definition about independent, so like I'm just gonna put it as a note. Okay, so if A and B so if A and B are independent, okay, so if A and B are independent, then basically if you have that they are independent, that means that P of A times P of B is equal to P of A intersect B. So if that's the case, then you have that this really does change your formulas somewhat. Okay, so if P of A and B are independent, then their product is basically just equal to the intersection. Okay, so that's kind of interesting because you have that all that you would do to find the intersection is just multiply them through. So in that case, one way that we can look at this is that if we were to consider another example, okay, so this next example is pretty, it's a pretty classic problem. So let's say that a manufacturer of gym equipment happens to know um, that 10% of their items are defective. So whenever we look at a problem like this, we'll just go ahead and say that the probability of a defective item is equal to 10%. So we'll just put 0.10. Now, the manufacturer happens to know that when a customer buys their product, only like about 30% actually use the product within the first year. So you have that that's going to be 0.30. Now, these statistics would actually be determined by it would be determined by the manufacturer because essentially they would happen to know their customers and whatnot. Now, if we were to assume that defectiveness of the equipment is independent of the use of the equipment, then in that case, we can actually find the probability uh, find the probability that a customer used the product and it is defective. Now, one practical application that you can kind of see about this is that this is more or less like a claim that a customer might make. So then that means that the manufacturer kind of knows how many of these claims are actually legit. So in that case, we have that the probability that an item is used and defective. Okay, so that means that all that you would need to do is just multiply through. So we know that it's going to be 0.10 multiplied by 0.30. So this equals to 0.03. So if you wanted to kind of interpret this, this means that for every 100 claims that are made towards the manufacturer, this means that only about 3% of them are actually legit. Okay, so in that case, that would mean that you have that if somebody happened to used it um, and it was not defective, there's actually a very high chance that it's gonna work and whatnot. Okay, so yeah, this gives you the probability that it's been used and that it is in fact defective. Um, okay, and then yeah, basically you could essentially you could probably, for instance, generalize this. So you could probably generalize this. So like if you say um, like general. So like if you said that you looked at the general multiplication rule, and you just say for n independent events, then in that case, if you're going to generalize this, then basically that means that you have that the probability of an event, let's say like A1, and then you have the probability of A2, and then basically you just repeat that however many times that will be. So in this case, it's n times. This is actually going to equal to the probability that A1 intersects A2 intersects, and then basically you're just doing that for all of the events. Okay, so you can actually generalize this essentially. Um, Now, consider this though. Okay, so let's say that uh, a family has 6 children. Okay, now let's say that we want to find the probability the family has at least one uh, one boy. Okay, so this is actually pretty interesting because basically we have that there are several ways that we can do this. So for instance, let's go ahead and say that the assumptions that are going to be made is uh, that a child being born, it's going to be one half that it's a boy. Now the other is that each birth has to be independent. So we have 6 independent births. So like if you were to think about it, you would have boy, 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 and then you could have like boy, girl, girl, girl. But note that basically, then 6 children. So like, let's just add on some more. So let's just say like girl, girl. Okay, so this is the idea of one boy. No, actually 6 boys. Sorry, 6 boys, and then we have one boy. Now this is actually going to get a little complicated because you have that essentially the sample space is going to be very big if we happen to do that. Okay, so this actually might take too long. So if we just assume independence, then in that case, this is actually going to be a lot easier. So here's what we'll do. We'll actually compute the probability that a boy is not born. So in that case, that's one half still. It's for the girl. Now, what we'll do is we'll just actually say that if we can find the probability that no boy is born, then in that case, we would just need to do this idea of girl, 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 girl. So in that case, you have that all of the births resulted in all girls. So what that means is that you would take the 1 minus p, which in this case is actually 1 half, and you would raise it to the 6th power. However, we want to find the probability of at least one boy. So that's why we're finding the probability of no boys. Because if we can just subtract that from 1, that's actually going to tell us the probability of at least one boy. So if we do it like this, then in that case, that's going to be okay, so all that we need to do from here is just really just figure out what is a half raised to the sixth power. Okay, but we also need to subtract that from 1, so we'll just add that to 1. Okay, now I'm getting that it's approximately, okay, so we have that it's approximately, um, it's actually very high. Okay, so let's go ahead and put it like this. Okay, so we have that it's approximately 0.98 44. Okay, so it's actually pretty high percentage that a family has at least one boy. Okay, so that's quite a bit in actuality, like in case of like, if you were playing the odds, that you're just like, okay, I want the family to have, that scenario of that there's just the one boy or even possibly two boys, three boys, four boys, and so on. Um, so in any case, like it would be very similar if you were playing with dice or something like that. Um, Now, interestingly enough, there is a way to actually figure out, for example, if you think about it like this, because there is another way. You could actually consider the total sample space. So if you consider the total sample space, it's actually 2 to the sixth power. So in that case, like 2 to the sixth power, um, okay, so you have that the number of children or the number of possibilities that the family could have is 64. So you have 64. Now, think about it like this. What is the probability that they're all girls? So in that case, you have that the probability that there are no boys, okay? So the probability that there are no boys is actually just 1 out of 64. Now, in that case, you have that if you were to take, yeah, if you were to take the complement, so like if you have the probability of at least one boy, then that means that you're just taking 1 minus 1 out of 64, and that equals to 63 out of 64, which actually is approximately the number that we found up over here. So it's actually the same thing if we just, do it this way, actually. But it's really just preference. Now, we can conclude this topic of conditional probability by basically looking at a chart. Okay, so we'll just call this social media usage. Okay, so this is based on a age group. Okay, so let's say that we essentially have a set of age groups. So a set of age groups are defined as follows. You have 18 to 34, you have 35 through 44, you have 45 through 54, and then you have 55 and up. Okay, but we're just going to go ahead and put over here that we have a total. Okay, now we have that this does break down into whether or not the group uses social media or they do not. So we'll just put doesn't. We could put doesn't use. I mean, that's okay. Um, Now, we just have to kind of assume that this is all based on some type of random survey that did its best to avoid any type of bias. So, the first group has that there were 117 that said that they use social media, but then there was 33 that do not. So then in this case, we have that the total that we get over here is 150. Now, in the next age group, we have that there were 89 folks that said that they use social media, but then you have that there's 36 that said that they do not. So we have that that's going to be 125. Now, once we kind of, fill out some more of the age groups, we start to notice a pattern. So we have that 83 said that they do in the 45 to 54 age group. And then we have that 57 said that they do not use social media. So we have that this is 140. Now, the last age group, which is 55 and up, we have that 49 individuals said that they do use social media, and then 66 said that they do not. That total, it happens to be 115. Now, if we go ahead and we add the uses age group, or yeah, we add up the individuals from all of the age groups that actually do use social media, we have that that's going to be 338. Okay, and then for the age groups that all the age groups that said that they do not use, you have that that's going to be 192, and we're just adding across. So if we add all together all of the individuals within all of the age groups, we have that there's a total of 530. Okay, so 530 is the total. Now, this whole point is so that you realize that, let's say, for example, that we wanted to do a computation of, let's say, like the probability that an individual uses social media given that they were from the first age group of 18 to 34. Now, how do we do this? Well, to do this, you actually have to look at what is the given probability. The given probability is the 18 and 34 age group, which is 150. So I happen to know that it's going to be 150, but out of that group, you want to have uses. So that would be 117. Now, this means that basically roughly about 0.78% actually use social media, given that they were from the first age group. Now, if I look at my chart, I can see that basically as the age group increases, the usage decreases. So what that means is that I would expect that if I was going to look at a similar item, such as like if I wanted to look at um, yeah, what is the probability that the group uh, 55 and up uses? So we're saying that what is the probability that a randomly selected individual uses social media given that they're from the age group of 55 and up? So we're saying that it decreases. So we would expect that basically that it would be less. Now, we have a smaller age group, so that's only out of 115. So we have that that's going to be 115, and then you have that that was 49. Now, if you figure out what that is, that's going to be approximately 0.43. So we have that roughly about 43% use social media from the last age group. Now, um, if you actually were to switch these for whatever reason, like um, if you were to switch these for whatever reason, please note that you're computing something else. So, for example, if you happen to switch the probabilities, so like if you're saying what is the probability that a randomly selected individual is 18 to 34 given that they use social media. So this is a little different now because now you're finding basically out of those that use social media, so that's the 338, and then you're looking at the 18 and 34 age group, that's 117. So if you actually do that computation, you're basically going to figure out that that computation is going to give you something entirely different. It's going to give you 0.35, uh, it's going to give you 0.35 or 35%. So that's actually saying that out of those that use social media, that 35% represent the younger age group. Um, and then, yeah, you can do other computations if you want to. Now, the last one that we can probably look at, for example, is what if you wanted to look at the probability that they use social media, so uses, but that they're from the 45 to 54 age group. So in this case, you have that you would still look at you would still look at the bottom one, so 45. You have that that's going to be 140. And then you look at the top part where they use social media and they are from that age group. So if you do that, then you're basically just using 83 divided by 140, of which in this case, this equals to about 0.593. So we have that this is saying that more than 50% or almost like 60% actually out of that age group, that's how many use social media. Um, Now, if I was to possibly, for whatever reason, I look at the age group of 18 and 34, and I say that it's the probability that they're 18 to 34 and that they do not use social media. Well, if we kind of look at the numbers, we can see that overwhelmingly people use social media out of the sample group. So in that case, I would expect probably that it's going to be low. It's actually going to be very low. So we have from 18, yeah, from 18 and 34 age group that do not use, and that's going to be 33 out of 192. So if we look at 33 out of 192, basically this is going to equate to almost like 17%. So we have that the first age group of 18 to 34 happens to have a very small percentage of those that do not use social media. Now, the whole purpose of this last example was really to get you to look at this table. So if you look at this table and you saw the pattern that as age groups increase, that social media usage actually decreases. And then similarly, you have that with the doesn't use. Well, there's not really a pattern technically, but you do have that the doesn't use it seems to increase in age group as you get as you get into the older age groups and whatnot. Um, Now, basically, what that means is that these are not independent at all. That age group determines whether or not the person uses social media or does not. So in that case, this is actually an example of using conditional probabilities where they're independent. Not independent. I'm very sorry. I meant to say dependent. So we have the this is the example of a dependent situation. Okay, so that's kind of interesting. Now, as we get further into some more examples of probability, we're going to actually look at some examples where we still will look at some of the independence and whatnot. Um, but, you know, um, and yes, you will actually see the ones of dependency as well, but it requires like knowing some of the advanced counting techniques. So like those examples where we said that we had cards and it was dependent, that was actually very special. Um, Now, if we were to possibly look at maybe like selecting defective items and then not replacing them, then that would be another case of dependency as well. But you'll see like basically both of the situations of the events of which that it's usually kind of indicated in the first place. And you'll see this on, on some of the review problems where it might say, for example, what's the probability that that you have a flight uh, that leaves on time, or yeah, like what is the probability that a flight had been canceled given that it was already delayed and whatnot. So those are some kind of examples that you might use your conditional probabilities. Okay.